As a reminder for proofs, write out every single step in words and in math notation. Whenever you have to prove that something equals something else, don't ever work across this equal sign. Don't add or subtract or divide. Think of it as this is your problem and this is your answer. And then here were some of the hints we talked about last time. Let's simplify things by distributing and combining like terms, or if you have fractions, you may want to factor and cancel things. It also helps to convert everything to sines and cosines because we know how to convert everything to sines and cosines, and that will help you with this next new hint, look for identities. These are some identities that will help you along the way. This video is going to focus on these last identities, the double angle ones. I want to point out that cosine 2 theta can be written using any of these three identities. It is equal to cosine squared theta minus sine squared theta, or 1 minus 2 sine squared theta, or 2 cosine squared theta minus 1. You can use any one of these three identities, any one of these three formulas to replace cosine 2 theta. These other two options come from replacing your cosine squared or your sine squared with a rearranged Pythagorean identity. Let's do some proofs. All right, prove that these fractions subtracted equal secant theta. This is when it's really important to make sure you pay attention to what your angles are. You cannot just cancel this sine and this sine because this is a sine 2 theta on top and this is a sine theta on bottom. So yeah, they're both sines, but they're different sines. So you can't just cancel like that. So this is why it's important to make sure you write out your angles every time. You can't just write sin or cos. You have to actually put in your theta. All right, but what can we do? Instead, let's replace this sine 2 theta and this cosine 2 theta with the double angle identity. I will put them up here as a reminder. So sine 2 theta is 2 sine theta cosine theta, and the denominator is still sine theta. And for cosine 2 theta, you can choose which one you prefer. I generally use this first one unless I can look ahead at the problem and see that it's better to write it out in terms of sines and cosines, or just cosine. In this case, I don't think it matters. Let's just use the top identity because that's what I have in my notes, because that is the one that I usually go to as my default. So yay. All right, well, that didn't seem to help us whatsoever. Actually it did. Okay, so there's a couple things you can do here. We're adding fractions now, or subtracting fractions, so I can get a common denominator and add these and write them as one long fraction. Or before I do that, you may want to cancel these sine thetas. Because if I cancel them, it will make finding a common denominator a little bit easier. Not that it's hard the other way either. But now, they're both sine thetas. That's why I could cancel them this time, not the 2 theta mixed in there. So now I am adding two fractions together, or a fraction to some other thing. So now I am going to find a common denominator. And you know what that means. That means that I need to put a cosine down here, and whatever you put in the bottom, you have to also put in the top. So when I rewrite this, this will be 2 cosine squared theta minus each piece of this second numerator. And I can write the common denominator in the bottom. So now it's written as one big fraction. I found a common denominator. Boom, that's what I got. Okay, well, why did I do that? Does it look any easier to you, or can you think ahead and see what we're to do? Notice I have 2 cosine squared terms up top. I can combine like terms and add those two together. So if I have 2 cosine squareds minus 1 cosine squared, that means I'm just left with 1 cosine squared term on top. And I still have this plus sine squared, and it's still all written over cosine. And now you should always, always, always recognize this identity. Anytime you are adding sine squareds and cosine squareds, or even if you're subtracting, you should pay attention to see if it's a rearranged form. This is the Pythagorean identity right here. I can replace that top part with a 1 because that is the Pythagorean identity. And now, let's look ahead or look back at what we're trying to find. We're trying to get this to equal secant, and we have 1 over cosine. Oh, pretty close. All we have to do is convert or use the reciprocal identity to get that to be secant. And now we have completed the entire proof. Okay, so some of the time I will have the 2 thetas already in the proof and you have to replace them with their identities and simplify. But some of the time you're going to kind of be working backwards. You're going to have to notice you have something like this in your proof and say, hey, that's the sine 2 theta identity, or hey, that's the cosine 2 theta identity. Don't get it confused with Pythagorean. Make sure you pay attention to the sign here. So let's do one proof like that. And then we will do a little bit of practice simplifying in case the proof did not make sense to you. So let's show that this equals or simplifies to 1/2 sine 2 theta. This one's a little bit tricky because it's not a straightforward sine 2 theta. It's a 1/2, but we got this. We're going to do it. We'll be fine. Okay, so in general, when you see this, what would you think to do? There are a couple of different things you can do. You can distribute your tangent. You can convert everything to sines and cosines. I am going to use my Pythagorean identity first. The rearranged Pythagorean identity replaces all of this in my parentheses with a cosine squared x. Side note. All right, that's what happened just then. That is the identity. I rearranged it to get all of this is equal to this. All right, now what do I want to do? Now let's convert everything to sines and cosines because I hate working with anything that is not a sine or a cosine. So we're going to convert, or your Alex homework says the quotient property. Tangent is sine over cosine. Because tangent had an x, you would use x's with your sines and cosines. And this is a fraction. I can extend the fraction bar to include the cosine squared. Why would I do that? Because now, notice you have a cosine squared on top, which is cosine times cosine. So one of those cosines is going to cancel with the cosine in the bottom. So I can cancel or use some algebra to cancel the cosine in the denominator with one of the cosines on top, and I'm left with sine x times cosine x. And yeah, this one's not straightforward. You might have gotten stuck, but then you look ahead and say, okay, I'm going to need to use this identity at some point. This is really, really close to the identity. If I had a 2 there, then this would equal my sine 2x. But I don't have a 2 there. So let's divide it over to the other side. And now I just kind of rearrange this identity to get this. Well, what is this? Our answer. So it may look a little weird and you may be like, what the heck, why would you even do that? The answer is because that's the answer. I don't know why you would do that otherwise. I know that's not a very good answer to give in math class, but because I'm told that this is my goal here, I'm trying to figure out how to get this in the same form of a sine 2x. And it's similar, if I multiplied this or divided my 2 over, it worked out. So that's how I knew to do it. I just looked ahead. I know that's not a super clear answer, but you're trying to just manipulate and rearrange as much as possible to get your answers. As long as you're using correct math, which you guys are great at, and I'm going to edit all this out. All right, let's practice doing this last little step here, this last simplifying, because I can see that it might be confusing. It might not, though. You may have understood that completely and been like, yeah, we got this. Okay, let's just practice simplifying some things. If I give you a bunch of different terms, I want you to simplify that. Can you pick out what the identity is? And I will put these at the top of our page again for us to see. Okay, so let's simplify. 2 times sine theta over 3 times cosine theta over 3. Oh, notice that is the same thing as this. Except I am using theta over 3's instead of a straightforward theta. Okay, so that means that this is equal to sine of 2 theta, but instead of thetas, I have theta over 3's. So your final answer, the way you would actually write that, would be sine of 2 theta over 3. You don't need the parentheses because we're not really adding anything. This is just our entire angle, but either one of these answers is correct. Sometimes the parentheses help you see it clearer, that it's all the angle. But there we go. That's it. I'm just trying to get you to recognize the identities and see that they're not always straightforward going to be thetas. All right, what about this next one? This is a cosine squared minus sine squared. I intentionally said cosine squared and sine squared without mentioning the angle because notice cosine squared minus sine squared is cosine 2 theta. But just like before, we don't have just thetas here. They have to be the exact same. If one was a 3 theta and one was a beta, that wouldn't work out. Or even like a 4 theta. They have to be the exact same. So cosine squared something minus sine squared something equals cosine 2 times that something, which is cosine of 6 theta. Or you can write it with parentheses. All right, this is pretty much the same idea. Cosine squared minus sine squared. Cosine squared something minus sine squared something is equal to cosine of 2 times that something. So actually multiply this out. What is 2 times 34? 68. And you can write it with or without parentheses like we did before. And then the last one, I probably should have had more of these, is sine something times cosine something. Hey, well that's kind of close to this. It's just like we did before. 2 sine theta cosine theta is equal to sine 2 theta. But this one doesn't have that 2 in front. So how can I rearrange this equation to get it to look like this? It's just like when we rearranged our Pythagorean identities to try and get them to work out for us. If I divide my 2 over, dividing by 2 is the same thing as putting a 1/2 in front, then sine something times cosine something is 1/2 sine 2 theta. So sine something times cosine something is 1/2 sine 2 something. I'm saying a lot of somethings, and hopefully you're catching on to what's going on here. That is our final answer. I probably should have done this one right after doing problem part A to see the slight difference here. In part A, I just straightforward, there was a 2 there, so I could just straightforward sub it into sine 2 theta. Here I had to divide by 2 before I could sub it into sine 2 theta.